Hello, welcome to this lesson of study of fluid dynamics. So, if you have not subscribed to the channel, you kindly subscribe. Okay. All right. So let's start. In this lesson, we'll talk about what we call the Bernoulli's equation. Okay. And so this equation is basically talking about a fluid flowing through a tube like this. Okay. At let's say point one, then to point two. Okay. So if you have a fluid that is flowing like this from point 1 to point 2, like I've said, and the pressure through the point 1, the first point to the second point, is given by this. Okay, this is how we get the formula. So the formula is this, like I've written here. I want you to just keep it, and we'll take examples and solve them. Actually, you can use the Reynolds transport theorem to prove this. A derivation, but the derivation is very long, and so let's know the formula and also know how to use the formula in solving questions. Okay. All right. So let's move to the next slide and solve questions there. Okay. All right. So the first question is: water flows at a rate of 2 meter cube per second through a tube with a diameter of 1 meter. If the pressure at this point is 80 kilopascal, what is the pressure of the fluid after the tube narrows down to a diameter of 0.5 meters? Okay, so water flows through at a rate. Okay, so let's underline some keys here, key points here. It flows at a rate of this, okay, which is 2 meter cube per second. Then you have the pressure at that point is 80 kilopascal, and at the point it narrows down to 0.5 meters diameter, and then the first diameter was 1 meter. Okay, so let's say if here is how the tube is. Okay, so at first the diameter here, d1, was equal to 1 meter, and we have the pressure at this point here to be p1, which is 80 kilopascal. Now the diameter at the second point is equal to 0.5 meters. And we are saying that the volume flow rate of the water is what? That the discharge is equal to 2 meter cube per second. Indeed, it was happening. The discharge was happening at the point 1. Okay, but the discharge will be for all the points. I will show you why. Okay, now we have the same water that is flowing through this thing, so the density for water is always equal to 1000 kilogram per meter cube. Okay, so you have this one as well given. Now since we know all these, we can solve it, because at point 1 it was water that was flowing through, so this will be equal to rho1, and at point 2 it's still water that is flowing through. It's at the diameter 2, so rho2. So rho1 and rho2, they are all the same. Now we are good to go. We are left with our height, and if you check the formula, we have rho1, rho2 we've been given as the density of water. We know P1, the pressure is 80 kilopascal, but we don't know U1, we don't know H1 as well. Now, since the question does not talk about H1, we assume that it is of level, meaning the height does not change. Okay, so it flows through the same height, it doesn't change. So it means that H1 is equal to H2, and sorry, let me talk to that one as well. Since it didn't talk about any heights, let me put it that way. Since it didn't talk about any heights, we assume that the pressure, that is the rho gh, the height pressure, rho gh is 0. Okay, we assume that it is not given, is 0. Okay, there's no height in we're not given gravity and a whole lot, so we don't have to consider that part as well. So the only part that is being left here is the u1 and u2. Okay, these ones. But we know from our mass conservation equation, that is the Reynolds transport theorem, that Ko, okay, let me use the pencil for this one. We know that Ko here is equal to, sorry, let me clean it and write it well. We know that Ko here is equal to UA. So we have been given diameter. We can calculate for our areas for both ends. Okay, so let's do that quickly. Alright, so at point 1, so point 1, okay, A1 is equal to pi over 4 d1 squared. Here we've done this in our previous lesson. That's the Reynolds transport theorem. So we say this will be equal to pi over 4, then d1 was 1 meter, so square it, becomes pi over 4 meter squared. Now at point 2, we have A2 to be equal to pi over 4 d2 squared, and this is equal to pi over 4 0.5 squared. So this will give me what? Pi over 4 times 0.5 squared. So it's the same as pi over 16, but let me check. Okay, 0.5 squared. Yes, so we have pi over 16 meter squared. So these are the areas we have. And now we know that from the Reynolds transport theorem, we're able to deduce that summation of the extensive properties at both ends or at the boundaries should be the same. Okay, or we can actually use that formula. In this case, we say that d delta m, I will erase this very soon, should be equal to ddt of integral rho u dA plus summation rho u a. And now here what you mean is, since nothing is changed, the density of the water is not changing, dm dt will be 0, and also rho is the same, so, and ddt of the whole of this, since nothing is changing, the property is the same, we'll get 0 as well. So this will be also 0, and so we find the summation of things at both ends is, for point 1 is equal to rho 1 u1 a1. Okay, if you sum this part, for point 2 we will get rho 2 u2 a2. So we sum all of these, it should be equal to 0, but point 1 is entering, so water is just entering that, so we negate it, and we say that rho 2 should u2 a2 should be equal to rho 1 u1 a1. But here rho 1 and rho 2 are the same, so we get this. But a2 u2 is what? Q2, and u1 a1 is what? Q1. That is discharge. So it means that K1 equals Q2 and is equal to Q. Okay, so we use the Q given to solve for all our U's. Okay, so very simple like that. I just wanted to prove to you how and the way we will be able to get our U's. Okay, so simply my U1, or let me write it, Q is equal to U A. So it means that Q, we are saying that it's the same as Q1 and Q2. So Q is equal to U1 A1, which will imply that my U1 is actually equal to what? Q over A1. And so U1 here will be equal to, what is my Q? My Q was given as 2, okay, this one, meter cube per second. So I have 2 over, then A1 is what? a1 here is giving us pi over 4, okay, which is equal to, when I divide this, I will get what, 2 over pi on 4. Okay, let me punch it on a calculator, I don't want any mistake. So I have 8 over pi, okay, meters per second. Let's keep this, okay. Now with the u2 is also giving us simply the same thing, q over a2, because they are the same. And so I have 2 over a2 is pi on 16, okay. Alright, so on 16, and that is 32 over pi meter per second, okay. So I have these a1, I know my u1, my u2, I know my density, okay, and I know my p1, okay. If you remember, we said, sorry, you use this formula, okay. So we know p1 is giving us this, and what we are interested in is p2, okay. We know our density, rho1 and rho2, they are the same, okay, so we don't have to suffer here. So we just set an equation for it. It's a p1 plus rho1 u1 squared over 2 plus rho1 hg, but you are saying that this part was not given, so we ignore it and say it is 0. We didn't talk about any height, so it means that the pressure due to the height is actually 0, okay. Alright, so this should be equal to p2 plus rho2 u2 squared over 2, okay. Alright, so if that is the case, then let's see, p2 here would then be equal to how do I call it, p1 plus rho1 and rho2 are the same, and you are calling them rho, u1 squared over 2 minus rho u2 squared over 2. So p2 here is equal to p1 plus, okay, then rho over 2 out, u1 squared, okay, u1 squared minus u2 squared. This is very simple for us, okay. So p2, sorry, is actually equal to, p1 is 80 kilopascal, so 80 kilos, and kilo is what, 10 to the power 3 times 10 to the power 3 plus rho, which is the density of water, and it's what, 1000 kilogram per meter cube, so over 2 into our u2 is, so u1 is giving us 8 over pi, which is 8 over pi squared minus 32 over pi squared, okay. Now this, we just go to the calculator and punch it, okay. So p2 here would then be equal to 80 times 10 power 3, sorry, plus half of 1000 is 500, then times, so you solve whatever that is in the bracket there, so 8 over pi, okay, I'm pointing everything on the calculator, squared minus 32 over pi squared. Okay, we get negative 97.2683. Let me put it that way. Okay, so if that is the case, then my P2 here will be equal to, just point is straight, 80 times 10 to the 3 plus 500 times the bracket negative 97.2683. Okay, so we have 31,365.85 Pascal. Okay, so P2 in kilo is 31 kilo, 31 point something, so 31.85. okay, 85 kilo Pascal. This is very, very simple, right? Okay, so let's move ahead and talk about the next question. Now with this question, it says the speed of water increases from this point 1.96, okay, meter per second to 25 meter per second, going from the whole house or hose to the nozzle. Okay, so let's say we have a tube and this is happening. Calculate the pressure in the hose, given that the pressure in the nozzle is 1 times, let me write it, pressure in the nozzle. Okay, and so let's say if the pressure in the nozzle is flowing from the house or the hose to the nozzle, so it means that if here is a hose and it's going to flowing from house to nozzle, here is 0.1, okay, and here is 0.2. So pressure at 0.2, let's start with the numbers here. You have 1.96 meter per second from the nozzle, so it means that U1, the velocity at the nozzle, is 1.96 meters per second, and U2 is equal to 25 meters per second. Okay, calculate the pressure in the hose, given that the pressure in the nozzle is, so here P2 is also giving us 1 times 10 to the power 5 Newton per meter squared. Okay, now given that the pressure is this, and assuming level, okay, level frictionless incompressible flow. Okay, now with the level, what it means is that there's no height in this. Okay, so it means the pressure due to height is also 0 as well here. Okay, with that level. Okay, and with a frictionless incompressible flow, with the incompressible flow, if you remember the flow phenomenon that we did in our discussion, second lesson in our discussion of fluid dynamics, we said that for incompressible fluid, density does not change. So it means that from point 1, ρ1 is the same as ρ2 in both. Okay, so if ρ1 is real, ρ2 is also real. Okay, we are saying that the pressure due to real GH, as in the pressure due to height, is 0. So it means Bernoulli's equation, which is being given by P1 plus ρ1, okay, U1 over 2, U1 squared rather, plus ρ1 GH1, okay, let me put it that way, equals P2 plus ρ1 ρ2 rather, U2 squared over 2 plus ρ2 GH2. Okay, now we are saying this part is 0. Okay, so here is 0. Now it reduces. You are saying ρ1 is equal to ρ2 and they are equal to ρ. Okay, since we are dealing with incompressible, so the equation will turn to P1 plus rho u1 squared over 2 equals p2 plus rho 2 u2 squared over 2. Now we don't know p1. P1 is what we want to find. Okay, if you remember, we didn't write anything for p1, but we have something for p2, which is this. Okay, the p2 is given, let me circle that. Okay, we have this. Then rho 2 is equal to rho. You did that. Rho 1 is equal to rho, but the pressure due to height is also 0. We know u1 given here, u2 given here. Okay, so it means that our p1, which we want to find, is equal to p2 plus rho. Let me say something here. This rho 2 here is supposed to be rho. Okay, so when you are doing, just okay, let me erase it. It's supposed to be rho. Okay, like that. Alright, so rho, then u2 squared over 2 minus rho u1 squared over 2. Okay, so it means that my p1 will now be equal to p2 plus rho over 2 out u2 squared minus u1 squared. Okay, now this is very, very simple for us. So we know p2, we know u2, u1, we know rho is the density of water given. Okay, so the speed of water, but density of water is always 1000 kilogram per meter cube. Okay, so therefore our p1 will be equal to p2, which was given as what? If you remember, p2 is given as 1 times 10 to the negative newton per meter cube, so meter squared. So 1 times 10 to the 5 plus rho over 2, which is 1000 over 2 into u2, which is 25 meter per second squared, minus 1.96 squared. Okay, if you remember, that was 1.96 was our u1. Okay, this is it. So you can use a calculator to punch it straight if you want. So 1 times 10 to the 5 plus 500 into 25 squared. Okay, 25 squared minus 1.96 squared, and this is equal to 621.1584. So the whole of this will give me 1 times 10 to the 5, okay, plus 500 times 621.1584. okay, and this is giving us 41 or 410,579.2 newton per meter squared. Okay, so this will be 4 points, then we count how many times, 1 2 3 4 5. Okay, so 0.5792 times 10 to the power 5 newtons per meter squared. Okay, I hope this is very, very simple. So this is how you calculate for your pressure in the Bernoulli's equation. Okay, so sometimes to all the questions we did, or all the solutions we did, these parts were 0. Sometimes you can meet them. Okay, so try to figure out, when the question is given, figure out what is 0, what is not 0, what type of flow are we talking about. Is it compressible, is it incompressible, is it the same fluid that is flowing through? Okay, so you ask yourself those stuff and you'll be able to be okay. All right, so thank you, and this will be the end of the Bernoulli's equation. Don't forget to subscribe to my channel if you have not subscribed.